preserving, depicting a rich water lane path that persisted long enough to sculpt landforms and create thick stacks of river lacustrine rocks. Okay, I cannot read that anymore. This rock illuminates a time when ancient rivers and streams on the surface of Mars physically and chemically altered the terrain and then transported and depositioned sediments in downstream basins. So it is my pleasure to welcome Mike. I'm sure he will tell us all about this and more. And keep in mind, you will have time to ask questions. I'm sure that the audience in here is very curious and will be asking questions that is relevant and maybe even extending the horizons of this research. Thank you, Michael, and welcome. The podium is yours.
Great, thank you for having me. I'm really excited to be here. Everybody can hear me okay? Check on that end. All right, great. So that was a perfect introduction, and I put together a quick little PowerPoint that I can go through, but maybe we can try to keep it informal. If you have any questions throughout, please just interrupt me. And if you're curious about anything, I'm not sure of everybody's background. I'm a geochemist, a sedimentary geochemist, so this will be really geared towards looking at the rocks more and exploring them with rovers. But I'll try to provide enough background that we're all on the same playing field. So if it's too much background too, just tell me to speed it up and stop blabbering. But anyways, I'll start sharing my screen and open up a discussion here. So can you see my screen now? Okay, great. And we already did the tech check and the every other check here. So this is just a quick little more introduction to me. I'm a sedimentary geochemist, and I am currently now Mars sample return scientist at Johnson Space Center. And so I grew up in Cold Spring, New York, so I'm not from Texas. So this is a new part of the country for me that I'm enjoying. I did my bachelor degree at Towson University in Maryland, and then my you're from Maryland? We got somebody?
Originally from Baltimore.
Okay, so you know Towson quite well. Yeah.
Yes.
That's where I grew up, or that's where I fell in love with geology there. I didn't know I actually wanted to be a geologist when I got there, and had a great professor there. So that was a lot of fun. And then I did my PhD at Stony Brook University out on Long Island, and then came here to do a postdoc at Rice University in conjunction with working at NASA Johnson Space Center. This was a NASA postdoc program. And from this postdoc, I got pretty lucky and got to work with the Curiosity rover. And so this rover landed on Mars in 2012. It's been exploring ever since. Some really great results. And I work on one of the instruments in particular. It's called the Chemin instrument. Looks at the minerals that are coming up from the rocks that we're looking at. I also do a ton of field work on Earth and try to use this as a reference frame for what we're seeing on Mars. And so that's kind of what the talk will be geared about today a little bit, is looking at Earth for sedimentary clues to what we're seeing on Mars. And like I said, right now I'm at the Johnson Space Center, but at the contractor company here, Jacobs. And my title is Mars Sample Return Scientist. We are getting ready for samples to come back, but in also doing so, we're curating samples that are curating pretty much anything that touched the rover before it went up. And these are known as contamination knowledge samples. So we want to make sure that we know whatever is Martian and that it's not Earth-based. So we need to have a kind of a baseline for the contamination that may go up with the samples, but another part of the project is also preparing for these samples to come back down. And this is my acknowledgement slide, just to kind of say that I wouldn't be here without any of the folks on the slides or this funding source. And there's many more that I haven't named here, especially my wife and kid who are outside right now taking care of the baby for me. So I appreciate their help as always, and family is very important to me. So this is kind of the outline of the talk here, but it's also the motivation that drives my research. I really look at sedimentary rocks of Mars, and we'll see, I'll show you that the ancient Mars was fundamentally different than what we see today. Right now, it's kind of this desiccated landscape. But ancient Mars had rivers flowing, had a ton of water at some point, and it looked more Earth-like. But what does that necessarily mean? And what does Earth-like mean is kind of what we're going to dive into a little more. And so we'll also touch on Curiosity's exploration of Gale Crater. And Gale Crater is where Curiosity's been traversing. It's kind of this big hole in the ground that a lot of sediments were deposited at some point from rivers, and it accumulated over time. And we've been kind of sampling this with our geologists on the ground with Curiosity. And so we're going to unravel some of the complex sedimentary stories by using the various tools that are on the rover itself. And then the last thing that I do is I look at terrestrial analogs, and I try to make a reference frame for what Mars looked like at one point here on Earth to kind of give us an idea of what Earth-like was when Mars had all these rivers running. And so for a geologist, this is an iconic picture here of Sicker Point. And the point of this picture is that this is really where kind of sedimentary geology and understanding uniformitarianism, which is just the fancy way of saying that the present is the key to the past. And a geologist, actually a farmer, walked upon this outcrop and realized that the rocks that were laid down here were older than the rocks here, and then something happened in time. And so can we use this kind of premise that the present is the key to the past to understand Mars as well? And I kind of turn this geological reference frame and say, instead of the present the key to past, is Earth the key to Mars past? And you'll see there's actually a connection between those as well. And so the next couple of slides, I'm just going to kind of go through and show you the evidence of water on Mars. I'm not sure if people are familiar with a bunch of these pictures, but they're just breathtaking to me. And I just thought it would be fun to kind of explore them and share them with you. And so this is Ebers-Wald D. It's one of the deltas that was absorbed from orbit on Mars. These deltas are formed when you have running water into a standing body of water. And so if you dried up the Mississippi River, you would be left with something that kind of looked like this. And it's remarkable to see this on the surface of Mars. And the resolution that we get is just increasing over the years. We've known that there's been water on Mars for quite some time. We've been exploring this ever since these canales were first drawn back in 1877. They were wrong at the time, but at least it started the speculation that there was water running on the surface of Mars. And so we've been exploring water on Mars since 1877. And since then, the resolution of these resolution of our cameras, resolution of the orbiters has just increased. You can see going from the Mariner 9 exploration, we can see value numbers here, all the way to the Mars Reconnaissance Orbiter over here, taking pictures of Jezreel Crater, and you can see a delta here. Just remarkable high resolution evidence that there was water on time from orbit. But we don't just see this from orbit, we also see it from in situ features from the rover. And so this is the Mars exploration rovers that took these really great pictures. This is at the Burns Formation on Mars. And you can just see these layers in the rocks that are punctuated over time. And you can see there in the backdrop here, they have different orientations. And this led scientists to believe that there was groundwater interacting with these rocks over time and that it was fluctuating over time. And so this was one piece of evidence from the Mars exploration rovers. But we also had evidence from these blueberries that we've seen. These are iconic blueberries that resemble very similar things that we would see in areas on Earth where we had water interacting with the rock itself. And these blueberries are more resistant material. So they didn't kind of dissolve away, but the other part of the rock did. And we're left with these blueberries behind. So this is another piece of evidence on the left here that is showing that there was water running at some point. And then on the right, we'll dive into this more. This is our study site for today a little bit, is this Gale Crater where Curiosity is. And in Gale Crater, we see these sandstones in the front of the picture here. Can everybody see my cursor too if I'm moving that? Okay. And then the backdrop here, we see these kind of finely laminate mudstones. And so this is another piece of evidence on the ground where we see that water was coming in and it was hitting the standing body of water. And when it does, it deposits coarse material like sand first, and then finer material offshore a little bit. And so that's where it deposited its mud. So just another piece of evidence that there was water from in situ, from rover missions. And then lastly, not only from seeing these actual features, but the chemistry of the rocks and the mineralogy of the rocks is also detailing that there was water running at some point. And so I work on the Chemin instrument, which is an X-ray diffractometer. And basically we drill into the surface of Mars, and this drill is probably about the size of a quarter. And it goes about, I want to say 3 inches or so. And we pick up a piece of the rock and we bring it back into the rover. We drop it off into the body of the rock, and then we bombard it with X-rays. And those X-rays are reflected, and from the reflections, it tells us what minerals are in there. So we get a great indication of what minerals are present, and each mineral tells us a unique story on what's going on. And my favorite happens to be these clay minerals. Clay minerals are traditionally formed on or in lakes in kind of soil, lake, earth environments, some that are very similar to what we might find in many fluvial or river, lake environments here on Earth. And so this was another piece of evidence from the mineralogy that was showing us that there was water there at some point. Then lastly, if we plot some of these, this is a whole representation of Mars here with some important secondary minerals here that indicate that there was water at some point. And phyllosilicates is another fancy name for the clays that I was talking about. But phyllosilicates are plotted across the globe on Mars, and it's just showing that there is plenty of water on Mars and that the history of water is rich. And so we know that there was water on Mars and that it looked Earth-like, but what does that really mean? And this is just an artist's rendition of what it may have looked like at some point, but we don't really have any constraints on that. What was the temperature? What was the precipitation? What was the altitude? What was the distance from the source that these things traveled? Those are all things that we don't have constraints for, and that's what my research kind of looks to Earth for sedimentary clues to kind of piece it all together. And so when I'm looking at Earth, though, it's not a one-to-one comparison, unfortunately. Mars on the left here, I'm showing kind of the evolution of igneous rocks that form from magmas. And Mars and most terrestrial planets are in this area called a secondary crust, which is really just fancy saying that Mars is dominated by basalt. On Earth, basalt is not that frequent on the surface. The ocean crust is made of basalt, but at the surface, it's not that abundant. And so this map on the right here is showing where basalt would be found on Earth, and these red areas, gray areas are a different composition. Many of us know from our countertops or what it may be is that Earth is really composed from granite, a granite dioritic kind of rock. So it's fundamentally different than what Mars is made of. And so we have to go to these unique places on Earth. A lot of my research goes to Iceland. I've done research in Idaho. I've done research in Hawaii. Pretty much, I would like to do research in every red dot around this map just to give us a better reference frame for what Mars is. But the fact that they are fundamentally different source rocks, that's kind of portrayed into the sedimentary rock record. If you start with something that's very different, when you weather this with environments like rain and chemically alter this material, it's going to be highlighted in what we see in the sedimentary trends. And so that's what this image here is kind of portraying. On the left is what we call a weathering profile. If you were just going to an outcrop, kind of driving through an outcrop on the road or something like that, you might see a weathering profile. That's what they're called. And when you have soils forming on top of rocks, this is what you get. You get this assemblage of secondary and primary minerals. But if you're starting with something very different, like on Earth, you start with things that are quartz rich, and on Mars, you're starting with things that are more pyroxene rich. You're going to end up with very different sedimentary trends. And that's just what I'm trying to emphasize here. I heard a mic open. Is there any question? Okay. So like I said, I want to pretty much go to every red dot on this map up on the right here. And that's kind of what my research for this past year has been detailing, is compiling any evidence that we have so far across the globe in various temperatures going from cold to warm. So mean annual temperature is abbreviated MAT, and mean annual precipitation is abbreviated MAP. And so I went across the literature as well as traveled to some places myself, and I'm looking at weathering profiles. So those are really just soils, as well as fluvial sediments. So those are just river sediments, lake sediments across the globe in different kind of climate regimes. And I'm going to compare it to what we see on Mars to maybe give us an idea of what that Earth-like Mars looked like and what the temperatures were perhaps at some point in ancient Mars. To do so, I use this chemical weathering index. I don't need to get into it too much, but basically it's just measuring how much elements you keep in the sample versus how much elements you lose in the sample. And when you go from something like an igneous rock, so a basalt, to something that you commonly see in soils or kaolinite, this weathering index increases. So it's just a way for us to quantify how much weathering is going on in the system itself. And I'll skip this part. This is just showing the grain size I look at. So on all these plots here, I explore various variables that may impact chemical weathering. And again, I use this CIA, our extent of chemical weathering here on the y-axis, against various environmental as well as climatic variables. And we see here elevation, we see depositional site and distance. And I really wanted to hone in on what the environmental conditions were in ancient Mars and what affects chemical weathering overall. And so if you first look at elevation, maybe it has some impact on these samples that we see from Hawaii, but it certainly doesn't have an impact as much as we would expect with some samples that we see from the Cascade Range in California. Then if we look at depositional site is really just looking at kind of currently in the river, what's up on the floodplains, and then what's even further off on the floodplains. And so if you're looking at depositional site, it has an impact, but not as much of an impact as some other variables that we'll look at. And then distance from the source is really just when you start in the upper reaches, when you start in the mountains, and then you carry the sediment downstream. Does this have an impact on the degree of alteration as well? It does a little bit for some sediments, but it doesn't for all sediments. So again, this variable was kind of ruled out as not being the most directly correlated with weathering. And then we get into some of these other ones. Maybe Provenance Age, which is just talking about how old the mountains are. And maybe Provenance Age has something to do with the degree of chemical weathering. And I didn't find much evidence for it to be there. What about precipitation? Precipitation definitely has some effect on the degree of alteration, but it only seems to affect it kind of early on. When you don't have much precipitation, you're not that weathered. But once you get a little bit of precipitation, it doesn't really matter. You start to get alteration values that are very high. So precipitation didn't matter all that much. The one that mattered the most, at least in my most recent study, is temperature. And so here we have temperature and we're comparing various environments. We have Antarctica over here, Iceland, Idaho, Hawaii, and we're looking at the degree of weathering in each of these environments. We can see that it's correlated with temperature in that it's directly reflected in the degree of weathering between these materials. And so temperature is kind of the winner in this case of variables. Although I will say that they're all intimately mixed in that we still need to keep working on this and to not rule out these other variables. But for the sake of simplicity, temperature definitely has the most important variable to look at. And so I'm going to compare this with our Martian field site here, which is Jezreel Crater. And this is our Curiosity rover. And on the right here, or in the middle plot here, is where Curiosity landed. I took the liberty on this picture, on this map, of where it landed to draw the ancient fluvial system that was coming in. So we had an ancient river coming in, it deposited all its sediments, and it made this fan shape that we see from orbit. And so Curiosity landed around here, and this line is where it's traversing. And so the first area that it really interrogated with a lot of detail was called Yellowknife Bay. And it started marching up to this group called the Mount Sharp group, which is this really high stack of sedimentary rocks in the middle of Jezreel Crater. And so we will, on the right here is kind of, if you're looking at all the rocks that it's traversed over so far, this is what they look like in a cross section. And the area that we'll focus on is the sheepbed area where it first started looking at down here, and also this Pahrump Hills area where it traversed probably 100 days or 1,000 days into the mission. And if we look at those areas here, we have Pahrump Hills and we have sheepbed here. So those two areas I just emphasized here. And we don't know the temperature. So let's plot the temperature for this across the whole range of potential weathering, or across a whole range of potential temperatures. But we do have the geochemistry here, and we do have the extent that we see that it's weathered. And so if we plot the range that it's weathered on the y-axis here across this whole X range, and where it intercepts with these lines that we created from our terrestrial environments. So from Iceland, from Idaho, from Hawaii, we can kind of start to develop traits or characteristics on what the paleoclimate may have been. When these rocks were formed, what did the climate look like? And if we do that, we can kind of say that these rocks were cold, probably Icelandic-like, and even colder at times. And so the moral of the story for me out of this paper was that Mars was once Icelandic-like and even colder at times, and the climate fluctuated. We can see that these rocks are probably colder than these rocks were formed. And so that was an interesting outcome from this paper. And so we have a context for the sedimentary rocks on Mars, but what does this really say about the history? I'm currently working on a paper where this was the traverse before for Curiosity, and this is Mount Sharp. So we've been climbing up further up Mount Sharp than what I showed before, and we're in this area now called the clay-bearing unit. Clay-bearing unit was identified from orbit as having a lot of clay minerals there. Is really the reason that we went to Gale Crater in the first place. And so I've been in charge of kind of detailing the mineralogy and the geochemistry for this clay-bearing unit. It's called the Glen Torton region. We name a lot of things in this region from Scottish origins. And so if we kind of develop, we have a climate model from what these rocks look like. But if we try to piece together what the sedimentary history looked like, I kind of came up with some model like this, where we have various time events coming in, and we have rivers coming in and streams coming in and depositing our sediments in the first kind of step of the whole piece of the puzzle here. And then over time, we actually have lake waters that are infiltrating into the sediments, and they're mixing with groundwaters coming into it as well. So we get a unique system that's developed subsurface, creating a unique geochemical and mineralogical gradient that we can see today with the rover exploration. And then we kind of have wind dunes coming in, and these wind dunes are cemented over time, just showing you that it's a complex sedimentary history. But if we use Earth as a clue, we can develop these models and kind of get better constraints on what it looked like at some point. And so where do we go next? We're headed to Jezreel Crater, or we landed at Jezreel Crater, which is really exciting. And I love this picture because I think it's just a beautiful representation of Jezreel Crater. Here is the river coming in. We have a delta over here. The rover landed somewhere around here. And this is where we'll be exploring with the next rover. And it has a unique set of capabilities that exceed what we currently see with Curiosity. And so it's going to be an astrobiological kind of representation. We're going to be sampling rocks here and bring them back to Earth for the first time ever. And that's what I'm excited about, because that's what my current job is preparing for us to, once we get these samples in hand, how are we going to get the most out of these precious samples? And so that's what my work details. And I'll take some final look backs here at Gale Crater again. And this is the rim. This is kind of the terrains that we traversed since landing in Gale Crater. There's some final thoughts here that I can just leave up, but we kind of went over it all already. But I will put up my contact information and a website here if you ever want to personally reach out to me. Any questions here, if you just want to talk about Mars in general or what we see on Earth, I have a blast talking about this stuff. So feel free to always reach out. And I appreciate you having me today. And if there's any questions or chat, please jump in.
Can I ask a question, Svetlana?
Please.
Okay, my name is Kumar Krishan, and I'm really excited. You know, you opened up my eyes, because from last 40 years now, I can see pieces are coming together quite a bit. And my question may sound weird, but I still am going to ask it. Let's say for 2 minutes that, you know, I also try to excite people about space exploration, particularly Mars exploration.
Mm-hmm.
But do you go by Mike or Michael?
You can call me Mike. That's fine.
Okay, so Mike, the question I get normally asked is, okay, Kumar, let's assume that we know everything about Mars. Its water, its history, its geology, its chemistry. What does it mean to us here when we are having COVID-19 and hundreds and thousands of people are getting dying and we don't have enough food and all that. How do you, I'm trying to see how to relate all this research to answer the question. It's very important.
Yeah.
Thank you.
Yeah, that's a great question. And I'm first going to throw this up here because there's a couple different ways that I like to answer that, or that I like to think about that. And the first is that this is a geological timeline here. Earth is up here in the blues and the greens, and we're going from old times to present day Earth. And we can see that Earth's record here, we have the oldest sediments dated here. We have the oldest potential stromatolites, so these microbes that are preserved in the rock, dated around here. But we really don't have the rise of the biosphere in the sedimentary rock record until very early in our geological age. And that's because all of our rocks are weathered. And Earth does a really good job of recycling things over time. It kind of, because we have water, it's subducting things.
Mike,
and we
can you share your screen? We can't see the screen.
Oh,
yeah, Mike,
you.
I was going to say that you're pointing, looks like you're pointing to this something on the screen, but we don't see it.
Oh, what a
Can
bummer.
you,
Let me try again. What do we got here? So I'll share my desktop. What do you, so now.
okay, now we see the green, yes.
Okay.
We see the Mhm.
Thank you for interrupting on that. I would have kept talking forever. So you see it now, right? Okay. So here we go. Here's geological timeline again. I think you heard most of it before, but these are Earth is oldest time from youngest time. And the point I want to emphasize here is that we don't really have much evidence on the biosphere, so microbes and stuff, until very early on in the Earth's history. If we go to look at the Mars rovers and the rocks that they're exploring, they are around this time, and Mars geological time is in reds and oranges here. This is the rocks that we're exploring with Mars. And this is the evidence that we have for the oldest kind of sedimentary rocks that we see so far in our solar system. So Mars does a great job of preserving rocks that interacted with water very early in our solar system, and Earth doesn't have that evidence. And so kind of looking at the rocks on Mars gives us an indication of what's going on with water in the solar system. But if we're also going to look for life, it is the oldest sedimentary rocks that we have, and could, if there was life, I'm not saying there is, but if there was life, it would give us the oldest clues for life in our solar system that we don't see on Earth. So that's one aspect of it that I think is important to kind of continuously bring myself back to. But I also think it's important to see how precious our environment is on Earth. And so when we're talking things about like climate warming or climate change, what it may be, Mars lost its environment and now it's a desiccated landscape. Earth didn't. And so it shows us how precious Earth is. And maybe it gives us a little different perspective on how we treat Earth or what we're looking at. So that's a third thing that I look at, or a second thing I look at. And the third thing I look at is the technology that we use to get to Mars only pushes the boundaries and the engineering that we have here on Earth, because we're landing a rover on a planet that takes us 8 months to get to, and we're landing it kind of on the size of a football field, and we're going to fly a helicopter there soon too, within the next week. And so this is pushing the technological boundaries for what we can do and the engineering boundaries for what we can do too. And so on top of pushing those boundaries, it's also just pushing human curiosity. I think it's exciting to see how many people watch the rover land, how many people are excited about Mars science, and including everybody on this call, I'm sure. And so those are the kind of things that I try to relate to people to emphasize why it's important to be studying what we're studying. And I hope that answered your question a little bit.
Thank you, Mike. Yes, it did. Thank you very much.
Good.
And I just want to add to what Mike's great explanation, that knowledge of the past makes us better and prepares us to build future. We cannot live in just a moment in time. It's everything that we know or we have not known, and if we can acquire that knowledge, just makes that much better for us to live in the future.
Great. Thanks for that follow-up. That was perfect.
Hey, Michael, this is George Salazar. Good presentation. I have a question. I'm just curious. Earth is called, I think Earth and Mars is somewhere in the vicinity of what they call the Goldilocks zone. And I'm just curious if the location of the planets, whether it's Earth, Mars, or Venus, which is pretty much in that area of the Goldilocks zone, so to speak, if there's any correlation of all this sediment and its location relative to areas, relative to the Goldilocks zone.
Yeah, George, that was a great question. And that Goldilocks zone too is also referred to as kind of the habitable zone too. And so different planets are kind of on the brink of it or whatnot. And so Earth is definitely positioned and poised for a very habitable environment. And I think that's where this Goldilocks zone is, because you need water to be running to kind of generate these habitable zones. And so I think the position definitely plays a part in it. You need to have liquid water running at some point. And so they create these unique environments that microbes could flourish if they were there. And so how close you are to the sun, how close you are to having liquid water running is all within kind of that zone that you were talking about, the Goldilocks zone. So I think, I don't know if I answered that fully, but that's definitely part of the reason that we see a rich sedimentary rock record on Mars, is that we were able to persist and have water running at some point.
Thank you.
Mike, where do you see the next? What is the next step, or maybe a step after that in Martian exploration?
Well, the next step is really with this Perseverance rover and the Mars sample return missions. And I don't know how familiar you are with it, but I'll just go into detail a little bit. Is that the Perseverance rover is the first of the three-part fleet that's going to bring back these rovers, or bring back these samples. And so the Perseverance rover is going to take the samples, and the samples are about the size of a pen. And a little thicker, maybe about the diameter of a nickel, or not a quarter, but diameter of a nickel. And so bringing these samples back to Earth and interrogating them with the instruments that we have on Earth is going to give us a whole new insight to what's going on the surface of Mars. And as sophisticated and as lucky as we are to land these rovers on Mars, we're also doing science with instruments that don't even come close to some of the capabilities that we have here on Earth. So bringing these samples back and being able to interrogate them with synchrotron radiation at a national lab will give us clues that we never were able to see before. And that's where we're heading. And so those samples won't be back here. There's going to be another mission that goes up. It's called the Fetch Rover. It's going to land on the surface of Mars. It's supposed to go up nominally in 2026. And so it will go and fetch the samples back. And then and it's going to kind of fire them off into space. And then there's going to be an orbiter that goes up and kind of catches them like a basketball almost and brings them back down to Earth. And they're not supposed to be here until early 2030s. And so that's where Mars science is going, by looking at those samples. But we also have the Perseverance rover, which has tools that we've never sent to Mars before. It has a higher resolution way of seeing the geochemistry. And so we have a unique set of tools with the Pixel instrument, with the Raman instruments that are on there. And so exploring this delta, the hierarchy of what we've explored with Mars were with the Mars exploration rovers were to find water, and they did that. The Gale, or the Curiosity rover's mission was to find habitable environments, and it did that. And now our mission has proceeded past that. We already know things were habitable, but now we're looking for life. And so this is an astrobiological exploration, and that's just what Perseverance is going to do. And it's got a tool set that is capable of identifying what they call biosignatures if they're there. But if they're not there, that's also pretty cool evidence too, that again points to like, Earth, you're pretty unique, and maybe we should take a look at that.
I have a question, Svetlana. Can I go ahead and ask? I'm
Sure,
going to
yes,
show you, Mike. Mike, I'm going to show you my ignorance. It looks like, so much water was there a few billion years ago on Mars.
Mm-hmm.
And I keep wondering, where did it go? Did it break down into hydrogen and oxygen and kind of leave the planet, or what? It looks like there was abundance, and I'm scared of that thing happening to Earth, although I won't be here in a few billion years,
Yeah.
Just if you could comment and
Yeah.
make me feel.
So that's
Right.
a fun question to talk about, and has kind of geological timeline scales. And so part of it is that Mars cooled down fast and it lost its magnetic sphere. And so it doesn't have the magnetic sphere keeps the atmosphere, helps keep the atmosphere in. And so Mars doesn't have kind of that magnetic dynamo. And so it started losing its atmosphere very early in its geological evolution. So when it's losing its atmosphere, it wasn't able to sustain liquid water over time. And so that's why it lost most of its water. Although there is a recent paper, and I'm talking within the past few weeks, that have showed a lot of these sedimentary rocks that we're looking at also suck up a bunch of water. So on top of losing some of those rivers because the atmosphere was lost, the sedimentary rocks suck up a lot of water too. And the reservoir for sucking up the water in these rocks is modeled to be a lot more than we previously thought. So some of the water is probably locked up in these sedimentary rocks, but some of it was also lost because there's no other atmosphere. On Earth, we can model how long the magnetic dynamo will work on Earth, and it's way out there, but it will shut off at some point. Just like the solar evolution, the sun is a star. The sun will expire at some point too, in terms of how stars evolve. So we're talking way down the line, but those are things that happen over geological timeline. So that's what I got for now.
How do you know that
Thank you.
How do you know that the water got sucked up into the sedimentary rock?
Yeah, great question. And that's a big part of my research, and what I enjoy talking about is these clays. In the structure of these clay minerals, there's actually water involved in it. And so if you plotted out where all the elements are in there in the crystal lattice, you can see that water is built into these structures themselves. And it's not just clays, the sulfates are another type of minerals that also absorb water too. And so if you look at the formula of it, for sulfate, it's calcium and sulfur and oxygen, but then it has maybe 5 waters involved in it. And so water is an integral part to the actual mineral structure that you're looking at. And so if we have an idea what minerals are there, we can kind of model how much water is absorbed to these minerals too, or within the structure.
Thank you.
Yeah.
Charles, do you have a question you wanted to ask?
No, I'm just amazed. I appreciate the presentation, and it's just really amazing how much we can learn from being so far away from a place. And even with the rovers and so forth, still it's just amazing. I
agree. Thanks, Charles, for sharing my excitement.
Dr. Thorpe, my name's Douglas Jezreel. I was teaching, I had a long career in aerospace there and with Honeywell and the NASA JSC community, and now I'm a teacher in public high schools, mostly a math teacher, and this year I'm a substitute teacher. I had a student at Lamar High School 2 years ago. She said, my grandfather worked for NASA. He was a photographer, and his name was Victor Roder, R-H-O-D-E-R, So I look on the internet to see what's a public document that I could publish on the AIAA Houston section website. He was hired out of Texas Southern University after going through the GI Bill. He was one of 5 photographers hired by NASA on one day in 1963, and NASA put out a press release. We just hired 5 people, and he'd been a photographer for the school newspaper. And there's a public NASA document. He and 5 other people on a NASA team went out into the desert with an 18-wheeler truck, and they slammed a drill down into the desert to see how far you can penetrate under a surface like Death Valley or Mars, you know?
Mm-hmm.
So in his short, less than 20-year career, he, you know, this report lists him as one of the 5 names on the team. And there's several pictures in the report that show some of the men there, but he's not credited as the photographer of those photos, you know. His photo is not in there, but he's one of the people on the team. And you see these really cool photos, you know. How is a drill going to penetrate in the desert and do it, say, 100 times? And what are the 100 different ways that it penetrates? Because underneath that desert soil that you see are a field of rocks and boulders. And every time you slam that drill down, it goes down a different way.
Mm-hmm.
And it makes a different kind of a hole there, you know, say it's 10 feet deep. And so they dig out the hole each time and see, you know, sometimes the drill went down straight, but then deflected 30 degrees. Other times it'll deflect 60 degrees, so depending on what it hit, you know. So way back then, they were doing all these cool experiments. And so the work you're doing, Dr. Thorpe, and the work NASA's doing currently, I thought Kumar asked a great question there, and you gave a great answer to that. Why do we do this? What good is it? Why aren't we spending this money in some other way? You gave a really great answer for that. So thank you for inspiring us today.
Thank you so much. And I appreciate you sharing that story. That's really cool to see. And I've had my own problems with drills in various locations too, where I'm trying to go down and, you know, I bought a couple $1,000 drill and used it once and it was broken. So, I mean, those are fun stories to talk about. Thank you for sharing that experience.
Yeah, and by the way, I looked up Victor Roeder Jr. on LinkedIn, and I said, was this man your father by any chance? And he answered me back on LinkedIn, and he said, yeah, that's my late father, and thank you very much for publishing that on the AIAA Houston section website.
That's great. I'm gonna look him up after this call. Appreciate you sharing.
Hey, Michael, George here again. I got a question. So we're going back to the moon, and you know, the moon is called the proving ground for eventually going on to Mars, and the proving ground is going to, I guess, provide the data to understand what it live and work on another planet. But you know, certainly moon composition is a little different than Mars. And I'm just wondering if I could get your thoughts on what are the limitations of the proving ground on the moon, and perhaps what we should be pursuing on the moon that will help us go to Mars, given that moon has its limitations in terms of geographical stuff.
Yeah, that's a fun question to talk about, because the moon is very different, but it's still made of basalt. And so we can still learn something about basalts in the solar system too by looking at rocks on the moon. But another thing that we use for Mars is this thing called crater dating. And crater dating is to kind of understand how old rocks are on Mars, but it started with the moon. And so we know how to model it. I'm trying not to get into the weeds here, but we know how to model how many times the moon was impacted, and we dated those rocks that came back, and we can kind of create a curve for how old areas are based on how many craters it has and how big these craters are. And so the moon kind of serves as a way to understand how old rocks are on Mars as well. So that's just the geological relationship that I think we can understand a little bit. But I think it's also, again, going back to the technology, is getting to the moon and building this gateway is part of the program as well, which is not the space station, but it's going to be kind of the halfway point between the moon and Earth's space station. So we kind of have a pit stop along the way. And so we can have people that are in moon's orbit, and we can have people in the space station, and we don't. Part of the problem of getting to Mars and why we need to go every 2 years is how close they are. If we have a jumping off point, a pit stop along the way where we could refuel or something like that along the way, maybe that increases our ability to get to Mars more frequent or easier. It's just not as far of a journey, and not as maybe we can change the planning a little bit. But that's really me kind of speculating. The moon's not my forte, so I wouldn't take anything I said take it all with a grain of salt. But that's kind of just what I'm spitballing.
All right, appreciate it. Thank you.
Yeah, I had a question. To take off on what Svetlana was saying about the next steps and what your directions are, and that's first of all a very good presentation of the description of what's on Mars and how it compares to Earth and that.
Thank you.
But I think the direction I would hope that you and folks in your same area would be shooting for is how do you use the soil on Mars and rocks on Mars to do what we need to do when we get there to sustain life and to make a first station on Mars. We need energy, we need food, we need water for sure, but also materials to build other things. And so one application I would think of your knowledge and your research is once you get some soil sample returns from Mars, is to branch into studies about how to use that. And like George was saying, also using the moon as a testing ground to perfect processes and procedures on how to use that to get the things that we really need on Mars to survive. And that is to make food, energy, water, and materials. So I would hope your career or your road to better understanding and utilization of Mars is also to improve our knowledge of how to use the soil on Mars to get what we need to survive.
Yep. Yeah.
And that life and searching for life is a nice byproduct, in my opinion. I'm an engineer, not a scientist, so I say we need to find out how to survive on Mars. And then if we happen to trip over some life, that would be nice to know. But the direction I would want to push is how to survive on Mars.
Yeah, so I think that's all really great points and something that I personally want to do. So you hit it on the head. And I think when Svetlana asked that question, maybe I was a little heavy-handed to what I'm doing with Mars sample return, but there are plenty of investigations going on we don't have Mars soil yet, but we kind of have an idea of what it might look like. And so they call it Mars simulants. And so we're kind of making Mars soil here on Earth, and we're trying to see how plants can grow in Mars-like soil. I think when we get the samples back, that'll give us a better evidence for how things can grow in the actual soil that we're seeing here. But those investigations are underway. Another key aspect of that is that on top of being able to grow things in Mars soil, which is different than Earth soil, we also need to factor in gravity. And so we're doing experiments on the space station, which has microgravity, very little gravity, and also Mars is 1/6 of our gravity. And so we need to do experiments on how plants grow in this different gravity, not just what the chemical properties of the soil are as well. And so that's another key area of research that we're going to explore. And there's a lot more than I said the future of Mars science is, and I got a lot going on in my head that I want to explore too. But those are great points, Mike. Thanks for bringing them up.
Mike, may I suggest that the Mars gravity is 38%, not 1/6.
Okay.
I believe 1/6 is the moon gravity.
Okay. Yeah, there we go. Thank you for that.
I loved your presentation.
Oh, I think you muted. Thank you for that.
I loved your presentation. I became so smart today.
I'm becoming smarter. You helped me out too. Thank you.
Hey, Michael, this is Mohamed. I wanted to ask a question about one of your earlier answers. I think you mentioned that Mars lost its magnetic sphere because it cooled down quickly. I was hoping you could explain that. I think that stems from the fact that I don't know where Earth's magnetic sphere comes from. So I was hoping you could maybe dive into that for me, please.
Yeah, and so this is going back to my early graduate level courses and understanding the inner core a little bit, which I tend to focus on the surface more. But just to sum up what I know about it is that the inner core is still, or I mean, the core and mantle are still active, and that's creating heat and convection. And so when the heat and convection come out of Earth, it starts to make these magnetic spheres going from the north to south dynamo, or north to south poles. And so that's what help keeps the atmosphere in. And that's also why when you go to places, Iceland, because I'm heavy-handed there, go to Iceland, you can see the northern lights. And the northern lights are solar rays that come down, and they're blocked by the magnetic sphere. And so they actually go around Earth, and they're not actually, they're solar particles, and they're not coming down and actually touching Earth too. So it's projecting around Earth in a circle almost. And so that's what keeps kind of the magnetic sphere going. And part of that interior heat in any planet is the elements too. And so they decay over time. So Mars, Earth, they all have elements that are called heat producing elements. And you can map out their decay over time with, just as if you were mapping radiocarbon for dating bones at some point, but instead we're mapping things that have a longer decay time. So potassium is one of these heat producing elements. We can map out how long it decays over time and how much the planet has potassium and how much heat is in the center of the Earth, or center of Mars, to kind of create that convection and keep the atmosphere in. Did I get too into the weeds there? Did that answer it?
That's a wicked explanation. Thank you. That makes a lot of sense.
I myself go in circles sometimes, so cut me off if I go too far.
Yeah, Don Nelson, got a question.
Hi, Don.
What influence would the composition of the atmosphere and the water make at the time that you think they had water on the surface of Mars?
Yeah, that's a great question that we ponder, because Mars' atmosphere right now is predominantly CO2. And so if you have an atmosphere which is really rich in CO2, that means that the waters that are coming down and precipitating are also going to have a lot of CO2 in it as well. And if you have a lot of CO2 and the waters that are interacting with the rocks, you're going to make a lot of carbonates. And carbonates are found in various places on Earth, caves, but they're also found in lake environments too. The surprising piece of the puzzle is that we don't see much carbonate on the surface of Mars. We do see it in select areas, and we're detailing on where we just uncovered it with the rover now, but it's not as abundant as we thought it might be. And so there's always been kind of a missing link where the carbonates, if it's a carbonate rich atmosphere. And so when we're trying to understand what ancient environment was like, and we're modeling what that atmosphere was like, we also have to take into consideration where it's going to go into the sedimentary rock record too. So a sedimentary rock record, I always like to refer to as being our oldest history book. And if we look at that history book, it could give us an indication of what the atmosphere was like. And to be honest, the clays that we're seeing and the minerals that we're seeing, again, they look Earth-like. So how do we get to something that's making Earth-like, but we don't see all the carbonates? It's confusing, Don, and that's something that we're still trying to reconcile. And so I'm a geologist, I deal with the rocks, but there's atmospheric modelers that are we're at ends. We don't know how to reconcile our different models. The atmospheric modelers are like, hey, we need a bunch of these elements in the atmosphere to make it warm. We need different greenhouse gases, whether it's methane, whether it's these different things that are going to warm the environment. But the geologists are like, hey, we don't see that in the rocks. Like, how do we get these two together? And that's something we're still working on.
Thank you.
We're collecting samples, or will be soon, on Mars, but it's going to be over 10 years, I think, before you get a chance to look at them on Earth. What Mars missions do we have planned, or do you know of maybe other nations have planned between now and the time of the sample return? And which missions would be most interesting to you?
So I'm still very much interested in the Curiosity rover. It's living way past the timeline that it was supposed to. These rovers, the Perseverance rover's nominal mission is only 2 years, but we have some engineers in the group here, I think, and engineering is just remarkable. I don't know how they do it. They get these rovers to land on a planet, and it's way beyond my pay grade or what I'm able to comprehend, or how they can fix drills from Earth on Mars. Is really cool. And so I'm still very much invested in what the Curiosity rover is doing. It's just gone to a unique area on Mars that is a transition from one mineral we see from orbit to another mineral. And this transition may be kind of at the point where Mars started to lose its atmosphere. And so that may give us an indication of what's going on when it started to dry up. So that's what I'm really interested in still. But the Perseverance rover just touched down. It hasn't even gotten its first samples yet. And so we have many years ahead of us for Perseverance, including, and I think the engineers will love that, is how we're going to get the helicopter, the Mars copter, to fly in 38% of the gravity, not 1/6. Thank you again for that. How are we going to get this helicopter to fly in that? And so those missions I'm still heavily invested in, but there is also planning right now for the Fetch Rover. The Fetch Rover hasn't even been made yet to go get the samples. And so maybe there'll be some instruments on that. We're not sure yet. So we're still making the architecture for that Fetch Rover. There's also conceptual missions for just looking at the polar ice. So sending these smaller rovers that can kind of penetrate with radar into the subsurface to see if there's deeper ice anywhere than what we see at the surface. I don't know too much about them. So again, I'll probably lean on more with the current rovers. And then the final thing too is, I didn't talk about it, but the InSight mission. I'm not sure if anybody's familiar with that, but the InSight mission wasn't a rover, it was a lander, and it tried drilling into the surface. The drill actually broke a little bit, but it's still able to measure Mars quakes, well, earthquakes that they call Mars quakes. And so that is getting information on kind of the interior of the surface of Mars too, and kind of piecing this all together. I think before I know it, it's going to be 10 years later and I'm going to have those samples back in my hand. So that's kind of what I'm looking forward to. And time flies when you're looking at these things. And when I give presentations, I give in some outreach presentations to high school students. And I try to emphasize, hey, you guys, if you like this stuff, you'll be the first ones to look at it when it comes down, because you may have your PhD by the time the samples come down, but hopefully a little inspiration for the next generation of scientists too.
Yeah, well, thanks. I think I'd be near 90 years old when they come back. So I'm in Albuquerque. I assume that you know Larry Crumpler.
Yes, indeed. No, he doesn't know me, but I know the name Larry Crumpler.
Okay, yeah, well, yeah. I've known him for about 20 years.
Yeah.
We've had him speak to our section a few times. First time was before the rovers ever were launched. They were still trying to figure out where to land them.
Yeah, that's great. Yeah, I know of Larry's work in detail, but he won't know me, that's for sure. Oh. I'm just a young gun in all this still.
Well, thank you.
Thank you, Robert.
Say, Dr. Thorpe, I put a few links in the chat, the NASA documents, Mars penetrator testing in 1979 in the desert in Tonopah, Nevada.
Thank you so much. And I see your email here too. I can follow up with you.
Yes, Michael,
I want to
go ahead.
Touch on, relatively speaking, I guess, controversial subject. What is your opinion? So you mentioned that Mars atmosphere is mostly CO2. And so that's definitely not supporting human life. Just, we really need oxygen. You can't really get around it.
Mm-hmm.
And SpaceX plans to have some sort of a vehicle land to Mars in next, very soon. They're planning maybe next 3 years. So this is definitely expedited time frame. If you ask any other space agencies, not a commercial entity, for because the space agencies have a tendency to go a little bit slower due to funding and other hesitancy in making sure that everything is vetted and that you have ability not just to launch humans to the planet, but also return them back. Because advertising one-way mission is kind of difficult for government entities. So with all that said, what is your opinion? Is it actually a possibility within 3 years for for the commercial entity to safely launch, get the all the way to Mars, do whatever it is it takes to do there, and then come back with the same crew without any loss? What are the chances?
Yeah, so I'll preface this by saying that I'm speaking on myself and not part of the agency at all or anything like that. But I think it's ambitious. It takes a lot of energy to get to another planet, a lot of power to get there. That's why it's taking 3 missions to get the samples back. Not only because, I mean, we only have enough fuel to get up there with the rover, which is about the size of a minivan. And so if we're sending up humans too, you know, what, 3 humans fitting inside this minivan or something like that. But it takes a lot of energy to get there. And so there'll be multiple missions. I don't know how you could have the amount of fuel that you need to get to the surface just increases how big the actual the mission needs to be, which increases just the weight of the mission overall. So there's constraints there. And from my actual side of it is that the Perseverance rover has this instrument on it called MOXIE. And so MOXIE is taking the CO2 atmosphere and seeing if it can make oxygen. And so this is just a preliminary step that is part of the rover. And why not see what the results of that are first? And why not see what we get back from these rocks before kind of sending precious humans to another surface? So I err on the side of, let's make sure that we're doing it right before jumping the gun and doing it in another nature. But at the same time, these private companies are pushing our abilities and pushing the next front, like landing the SpaceX being able to land the rockets back down on, and not just discarding them has saved a tremendous amount of money too. And so private pushing the government too is also a big thing. And I think it's going to keep bringing us to the next step, and working in concert with these companies is only bettering our exploration of space. And so that's kind of my takeaway from it. And I err on the side of, I want to see what the rocks tell us first and what the MOXIE instrument tells us first, but also pushing the boundaries is a fun thing and good for exploration. So we'll see where it goes.
I had a question taking off on what Mohammed was talking about in the magnetic fields. And so since Mars doesn't have a magnetic field, you get unprotected radiation from the sun. Mm-hmm. And that's a major hazard, so much so that they're thinking that what we need to do for Mars is find a tunnel and live in a tunnel. And so I was wondering if you had any thoughts about how to make an artificial magnetic field around Mars that would eventually be a protection against that radiation.
So a couple of things. I'll first comment on the tunnel, because I've done some work myself, and this was more geared towards the moon, but how do we protect astronauts against this radiation? And so we went to Hawaii, where we were looking at these lava pits, which are these tunnels. So you have lava going over or underneath the surface, and it carves out a nice little tunnel. And so if there was some sort of large scale radiation coming towards these astronauts, could they go into one of these tunnels? And can we find it without actually seeing it? They call them kind of skylights. Can we find these skylights to get into a tunnel before seeing them? So that work's really interesting to me. And that was more towards kind of boots on the ground for astronauts on the moon, but it could certainly be applied to Mars as well. As for making a magnetic sphere, I am along the lines of a geologist in the sense that, like, don't mess with Mother Nature. I don't think that we would be able to make a magnetic sphere that would be sustainable. And then if we were able to do something like that, what are the implications past making that magnetic sphere? So I don't know. I tend to say let's leave Mother Nature on its course, but there are studies out there of kind of just like, I just watched one the other day, and this isn't my study and it's nobody I know in particular. I just read it and saw them present on it. But just like they talked about iron fertilization of the ocean to kind of increase productivity for climate warming and radiation, and a way to slow down climate warming. They were proposing that we release kind of iron particles into the atmosphere that would kind of keep the ability to sustain a climate on Mars by having these iron particles in the atmosphere, iron oxides. It was a little over my head, the whole presentation, but there are studies going on about that. I just don't know how to do it myself. And I'll just go back to my first point of probably saying, I'll let Mother Nature run its course on that one. But protecting from the harmful radiation is definitely something that we need to factor in when we're going to these planets, not just the inability for us to breathe on the planet.
So you would not be too keen on the whole area of terraforming Mars to make it more Earth-like?
I'm not necessarily like so that's a tough one. I'm not like, again, if I saw a study, I'm a fan of science too. If I saw a study that showed that it was possible, I would believe it. But right now, I think it's losing its atmosphere quicker than we would be able to replenish it. And so I don't, there's been nothing to me that's showing that it is a logical explanation yet. But if a paper came out and it was convincing to me, then I'm easily persuaded, but it needs to be, thoroughly interrogated before I would jump on board and say like, yeah, it's a possibility. So, I'm trying to say, Mike, I'm not trying to,
Yeah, I agree with you. Yeah.
Yeah.
And when there's some, when we do have a station or some people on Mars, especially from other countries like China and so forth, it would be difficult to start monkeying around with the nature of Mars because we might affect their life, of course.
Yeah.
That's in the future. I'm
Yeah.
sure there'll be some discussion about that some other time.
Yeah.
Oh, I have a question.
I think
Yeah.
Olga, go ahead. I just wanted to make a comment. Yes, the exploration of Mars is such a multifaceted challenge, and there's eclipse or life support is one of them, but there's also preservation of life, and something that we didn't even touch is actual trip to the and come back, because it both requires again life support, but also like one of those things is food, and when we were calculating how much food requires, you really do not have a launch vehicle right now that is available to carry that much volume.
Yep.
And forget about the astronauts or crew members in there as well. Olga, now your turn. I'll mute myself.
So there's some related to just the previous discussion and to what you were just saying about terraforming and even like talking about sample collections and everything. So there are concerns, of course, about the planetary safety, and so that we won't pollute the environment where we're going. So that's one question is related to the whole process of sample collection. So I know, of course, it's all addressed there, so planetary protection, but I just wanted you to tell how you deal with it and how you consider planetary protection in your work. And another thing is related to magnetic field that doesn't exist on Mars. It's very interesting to know, of course, how and why it was lost, and there's other plans to do core drilling, and so to investigate and to see what happened and to see if and when Mars may have magnetic field.
Okay. Yeah. So those are great questions, and I'm gonna keep talking and forget what I want to answer. So come back to me if I forget some aspect of your question, Olga. But the first one with planetary protection, I think over the course of the next 10 years, we want to make sure that we keep Earth, and Mars. And so that's part of the research that's going to be going on. And we just kind of none of this would have been happening if Perseverance didn't land. And so since Perseverance landed successfully, that's really kicked off this Mars sample return kind of process. And we're devoting a good amount of time now to understand facilities that will house these samples when they come back, how to house them safely. And again, how do we make sure we keep Mars, and Earth, and that there's not contamination across them. And if there is contamination from, there wouldn't be contamination from Mars to Earth, but if there's contamination from the samples, the sample containers or something like that, we know what the contamination was, and that if we see anything, it's going to have to be a pretty significant finding for us to say that that was unique to Mars. So I think that's one aspect of it. And then the second one is to the core. The InSight mission was really geared towards understanding the interior more, and it was trying to drill down into the surface, and the drill actually ended up not being able to function as well. We're still getting evidence for kind of what's going on with the Mars quakes, and that will give us evidence of what's going on in the core. But that was the mission that was really stemmed towards understanding what's going on in the interior. And we'll try to piece that together with the Mars quakes over time. But when we get these samples back, another thing that we can tell about them is kind of looking at the minerals themselves. The iron minerals do a great job of pointing to what's north and what's south. And so we can see preserved in rocks on Earth kind of because Earth has, they call them, I'm going on a tangent here. They call them, we know that Earth's magnetic sphere has changed over time, and the north and south poles have flopped. And they're called these Milankovitch cycles, are the fancy name for it. But we only know this because it's preserved in the rock record, and we see it in the minerals. So iron minerals in particular point to what's north and what's south. I think if we're looking at the samples that we bring back from Mars, we can see kind of, and we can date those rocks too. We can see when it shut off, why, and that may help us piece together the story a little bit with looking at the Mars quakes too and understanding the interior a little more. So that's all I kind of got for it now. Olga, I hope that helped a little bit.
Yes, thank you. Yeah, it's just really cool to know why it happened and what happened and why it happened. I'm really curious about this tragic event.
Yeah.
So it definitely will help to understand more about the solar system. And anyway, thank you.
Thank you, Olga.
Hey, Michael, I guess this is Mohamed again. I had I guess, more of an ethical question on the note of your talking about leaving Mother Nature run its course, because that reminded me of Musk on Stephen Colbert's show when he talked about nuking the poles to create an atmosphere for Mars, which just intuitively sounds wrong, but I don't think I'd be able to articulate what's wrong with that if Mars doesn't have any known life yet. But I guess I would kind of agree with you that we should probably let nature run its course, but I think I was hoping you could articulate your ethical standpoint on why that's a bad idea.
Yeah, so I don't know too much about it, but I know the poles hold a lot of ice there. And so if you free up the ice, you're going to free up some elements within the ice. The thing there is just what happened. It's an avalanche of events that happen afterwards. What are it's a cycle. So you're not just freeing up the elements there, but it's a cause and effect of the longer term cycle of it. So you don't have ice at the cores anymore. What happens there? Do you end up melting and then comes and forms an ocean down below? I just don't know where the cause and effect down the road is versus what the means of it are. So to generate that atmosphere from nuking the poles, what does that do for weathering rocks down the line? Does that change? Like, for instance, I'll give you an example on Earth that I'm thinking of most frequently. Volcanoes emit gases from an eruption. Those are greenhouse gases that help warm the environment. And so when we can see in the geological record that those gases are warming the environment, but it also creates an adverse effect because it creates a blanket that doesn't allow the sun UV to penetrate. And so it's not just a simple problem of the gases help warm the environment, but we're also creating aerosols that don't allow light to penetrate. And so it's a plus minus there. And so I don't know if all the plus minuses have been calculated for instance, nuking the poles. And so I would err on the side that I need to see what all the plus and minuses are before jumping into something like that. And again, that's just the way my brain works, but I'm not sure. So I don't know if that answered your question, Mohammed, but that's what I got.
Okay, no, I think there have been plenty of historical examples of humans not understanding the unintended consequences of their actions to nature. So yeah, I guess that makes sense.
Yeah.
Thank you.
Matter of fact, that's a good point, Mohammed. And the unintended consequences sometimes it might be okay to do on Mars as opposed to Earth. Because Earth, we have 7 billion people and growing. But on Mars, it's just a rock right now. In my view, I'm an engineer.
Yeah.
But it's just a rock. And so we can experiment with a rock, right? And we can find out we can answer a lot of questions about planetary physics and how a planet works with Mars, and then understand what we want to do to Earth before we do anything that would upset any kind of balance and have unintended consequences. So in one view of Mars is that it's like a laboratory, and we could use that laboratory to gain knowledge and understanding, and then use that to protect and help the Earth. So it's not so much using Mars to populate, but to use Mars to gain understanding and get knowledge of the physical aspects of a planet.
Yeah, just to follow up on that, I think it's a great point, because it's just a different way of saying what I think too is that Mars can be kind of a control for Earth. Like, it's our control. We know that the cycle of water shut off at some point in its history. And did it have microbes? If it didn't, then we know that Earth is this unique and why. And so we have a unique time to compare why Earth is its way and why Mars is its way, and a compare, contrast, and a control. So kind of what you were saying, more or less, Mike.
Wow, this was great. Thank you so much for your presentation, for all the factual information that you have shared with us. And I can't wait to see what's next in both your research as well as the exploration of Mars. I know we have explored, we collective, obviously, that very small part of Martian surface. And there's so much left to explore and discover in there. So thank you for sharing all that you have done so far, and please feel free to come back and share what is coming, what you have discovered, new or even old, but we haven't yet heard. With that, thank you, Michael, and thank you everyone for joining today. Next week we have another speaker. It's Nancy Leveson. She's a professor at MIT, and her focus of her research is software safety, and specifically software safety within space exploration. She has participated in multiple investigations in previous in Columbia accident, for instance, and have looked and analyzed the shuttle software. And I can't wait to hear what she will be talking with us about next week, because it's especially interesting and concerning to me because part of my experience and focus that I am working with right now is creating autonomous software for Gateway, and that will be invaluable resource of information for as we are building the next outpost in the lunar orbit. So I appreciate everyone joining. Gary, I see you turn on your camera. If you want to, do you have a question, or you just wanted to show up.
I know. I wanted to thank Mike very much for that presentation on the Mars. You know, I've been following the human spacecraft program and everything. It's good to know that we got somebody preparing that future landing spot for us. And so that was a very good presentation. And I really hadn't understood much about what was going on because I hadn't been paying a whole lot of attention to the exploration efforts. So thank you so much.
Thank you, Gary. Thank you, everybody, for having me. This was a really fun discussion. So I appreciate that.
Yeah, and I'm looking forward to see you, everyone, next week. The same time, and here you have a link. So join us at SpaceGeekSpeak on Saturday morning.
Terrific.
Bye, everyone.
Bye, guys.
Bye-bye. Thank you.